Today, you guys, we're looking at 6.1. And actually, the entire chapter we're going to be looking at functions, compositions of functions. We'll be looking at rational exponents. We're going to be looking at radicals, so different types of functions. So this first section kind of gets us off the bat. And the first half of the day, more or less, is quite easy. So we're going to look at operations of functions. So we're going to be adding, subtracting, multiplying, and dividing functions. The nice thing about dividing functions during this chapter is we're not going to be worried about doing long division. So a lot of times we just divide the functions and we're going to leave them. We're not actually going to perform the long division to solve those. Okay, so that's going to be kind of a nice change of pace. But first half, again, adding, subtracting, multiplying, and dividing. And then there's a few things we're going to look at because we want to make sure our functions, or we're going to talk a little bit about our domain. So sometimes functions might look like these two pictures here, where up to this point, we've been doing polynomials, or last chapter. And polynomials, if you can recall, were smooth, continuous graphs. They went on forever in both directions. Okay, so our domain, and in this case, range, would have been all reals. Okay, it goes left and right forever, goes up and down forever. We're going to be looking at more specialized graphs of functions where sometimes there are restrictions to our domain and range. Okay, so here in this middle one, you can see that x cannot be 0. We have an asymptote here. Also, y cannot be 0 in the case of this graph. If we go over to the next one, looking at our domains, it looks like x is greater than or equal to 0. There's no negative x values, and y is greater than or equal to 0. Okay, so these are a couple restrictions. I like to call them red flag warnings. Okay, so the first one we like to look for is when x is in our denominator. It's in our denominator. Okay. Because remember, we can't divide by 0 in math. It's impossible, okay? And that's a situation right here. This is actually the graph of y equals 1 over x, okay? This graph here is a graph of the square root function, okay? So our second kind of red flag warning in terms of our domain is any even root radicals, okay? So if it's a second root, like a square root, it's a fourth root, sixth root, eighth root, we can't have negative numbers there because remember, a square root of a negative number is imaginary. Okay, so we obviously would see that on our graph. Okay, so those are going to be the two things to look out for today with our domain restrictions. So anytime it says, state restrictions on domain, if you don't see x in your denominator, if you don't see an even root radical, you can just say all reals. I'll show you how that kind of works out here as we move into example 1. All right. So as we looked up here before, all right, the notation might confuse people a little, but this just means we're going to add f of x to g of x. So we have our two functions. I'm going to take x squared minus 9, and I have 2x plus 2, and I'm going to add those two functions together. Keep in mind when we add two functions together, we're just combining like terms. So we have x squared plus 2x, and then minus 7. Then it says state any restrictions on the domain. Well, I don't see any division by x, and I don't see any even root radicals. So my domain's all reals. It's as easy as that. If we're subtracting our two functions, x squared minus 9, 2x plus 2. Again, same thing, just make sure you subtract or distribute that subtraction. We wind up with x squared minus 2x minus 11. And again, the same thing here. We want to look for any restrictions on our domain. All right. I don't see any even root radicals. And I don't see any division with x. So my domain is all reals. If you notice, both of these are quadratic functions. They're parabolas, which definitely supports the understanding the domain is all reals. All right. Moving on to multiplication and division again. with division, we don't have to worry about long division. And if we're multiplying, I'm going to go out on a limb and say, you know how to do this because we've seen it before. So when we're multiplying functions, we want to distribute everything through. We get x cubed minus x squared minus 12x plus 2x squared minus 2x minus 24. So we get x cubed plus x squared minus 14x minus 24. Again, as we look through these, any dividing by x? No. Is there any even root radicals? No. So my domain is all reals. So hopefully you guys are kind of seeing, all right, if you have no clue about the domain, what is probably going to be a really good guess? You guessed it, all reals, okay? Most of the time, I mean, I have 4 examples here, 3 of them, the domain's all reals, okay? So a lot of times, if you have no clue on the domain, a good guess would be all reals, all right? And then we're actually going to throw this one in here. So now we have f over g, or f divided by g. And like I said before, today, and actually for the rest of the chapter, we are not going to perform the long division right now to simplify this out, okay? So what I want you to do is leave your function like this, okay? And I know that's a little confusing, that you don't want to do long division, but this is going to help us figure out our domain restrictions, okay? Because if you look at this, we are now dividing by x. X is in our denominator. This is going to be a problem because if you recall, we can't divide by 0, okay? So I'm trying to think about, when is this function not going to work? Well, it's not going to work if x is -2. If -2 plus 2 is 0, I'm then dividing by 0, which is undefined, okay? So whenever you see something like that, you want to set your denominator equal to 0 and solve for any restrictions, okay? Kind of an aside, if you see something like this, you end up with, 2 square root 1x plus 3. Let me actually do that. 2x plus 3 plus 4, all right? If we were looking at a domain restriction here, remember, what's under our radical has to be positive. So I want to figure out what's going to make that 0. So I subtract 3 and divide by 2. So x would need to be greater than or equal to -3/2. So it's kind of that same idea, whether we have something in our denominator with x or something under the radical with x. We want to make sure and find that point where it equals 0 and then move on from there. Okay, so that's the first half of the day. Adding, subtracting, multiplying, dividing functions, and then stating any domain restrictions. Second half of the day is compositions. And don't let this confuse you, but compositions are just taking one thing and plugging it into another, okay? And the notation is probably the most confusing part. So as you see here, we're going to use that open circle. So f of g of x is how it's read. F of g of x is the same as this, right? So notationally, it's the exact same thing. If I want to do g of f of x, that's the same as g of f of x, okay? Right, or in there, so it's, they're not the same, okay? So it's kind of the same thing. We're taking a function instead of a number and plugging it in, okay? So we're actually going to skip down to the bottom half of these examples first, okay? So we're going to skip down to these ones first and show you kind of how it works with algebraic expressions. So when I see this, f of g of x, so sometimes it might help you to write it out like this. But what this means is you're going to take function f, which is 3x squared minus 1, and you are going to plug in, instead of a number, you're going to plug in the entire function g for that x value. And then you just evaluate and solve. So 5x squared is 25x squared times 3. It's going to be 75x squared minus 1. All right. Domain restrictions. I don't see any x in my denominator. I don't see any even roots. My domain must be all reals. All right. Same thing over here. We have g of f of x. That means I'm going to take function g, and then I'm going to plug in f of x for any variables I see in the question. And then you're going to simplify and solve. So we have 15x squared minus 5. Again, today on most problems, you're going to be looking at those domain restrictions. I don't see any even root radicals. I don't see x in my denominator, so my domain must be all reals. All right. So that's function compositions. The most confusing question today is going to be this. When we give you not the algebraic function itself, but we give you ordered pairs associated with a function, okay? And the best way I can describe this, as you have kind of this conveyor belt with two machines, okay? And we're going to be sending objects through these two machines. So with this first situation, okay, we're going to call this F. We're going to call this, oh, sorry, whoops, F of G of X. So we're going to send it into G first, then we're going to send it into F, because remember, F of G of X. Okay, so G is getting thrown into F, which kind of makes sense on this conveyor belt. So we have plug in a number into G, and then whatever we get goes into F. Okay, so what we have in this situation is as follows. So I'm going to start with G. Okay, if I plug in a 4, it goes into G, it comes out a 3. Okay, the question is, can I plug a 3 into F? Well, yes, I can. So if I plug a 3 into F, what number comes out on the end is a -2. So in F of G of X, we have the coordinate 4, -2. Okay, we'll kind of repeat that process again. Okay, so again, I'm starting with G. So I take my first point. 2 goes into machine G, or function G. It comes out as a -1. Does -1 go into F? Yes, it does. When it goes into F, it transforms into a -5. So we have the point 2, -5 that works. All right. We'll do it again. 9, 4. So if I plug in a 9 into G, it comes out a 4. Does 4 go into F? Well, yes, it does. If 4 goes into F, it comes out a 7. So we have the point 9, 7. And then finally, we have the point 3, 10. So I send 3 into G. It comes out as a 10. 10 goes into F, and it comes out as an 8. So we have the point 3, 8 in this function composition. So this one worked out really nicely. Each point of G worked in F. All right. So we were able to plug in 4, 3 to G. 3 goes into F. So we were able to get an answer. All right. So it worked with all of those points. That's not going to always be the case today. So I'm going to kind of reset this problem. All right. Again, like I said, it's not always going to be the case. So if I go the other way and I look at G of F of X, so that means I'm starting with F and I'm going into G. All right. So if I plug a 3 in, a -2 comes out, all right? Can a -2 go into G? Nope. All right, there is no input value that's -2, so that point is not going to work. All right, my machine jams, the machine shuts down, I get fired because it's not working. Just kidding. All right, then we start another point. We plug in a -1, comes out as a -5. Does -5 go into machine G? Nope. Machine jammed again. Today is really not a good day for me at this factory. Plug in a 4, comes out a 7. Nope. Machine jams again. And the last one, 10, 8. So I plug in a 10, comes out as an 8. That one did not work. Machine jammed again. So what you can do is say that. You could say empty set, which is that symbol. You could say no solution, but any of those cases. So that's kind of when we're looking at pairs of ordered pairs, you want to make sure you start with the one to the right, essentially, and see if it goes into the other one. Start with G, does it go into F? And that machine analogy is kind of the best idea I can do. If 8 is not an X value or an input value in the next function, it does not work, okay? Sometimes when you do these questions, you might have 2 points that work. You might have 0, you might have 1, you might have all 4, like we had on A, you might have 3, okay? So it is important you test each point individually because you could have any number of answers from 0 to 4 possible, all right? So again, that's the most confusing part of the day. Hopefully that machine example helped give you a little more context to the ordered pair question. But that's it. Assignments here. If you have any questions, feel free to ask during class. Otherwise, you are welcome to use the discussion board, but try and get the assignment done before the day is done. Best of luck. Hope all is well. Enjoy completing the assignment.